Okay, welcome to Lecture 2 for Unit 3. Today we're talking about chemical weathering. Okay, so we are still talking about weathering, right? The breaking down of rocks from larger pieces to smaller pieces. But instead of a physical process, right, where we're just breaking it down into different bits, we're talking about chemical changes here. Okay, if you remember anything about chemical changes, they're hard to reverse and they are a little bit more permanent. Okay, so chemical weathering is a process by which rocks break down as a result of chemical reactions. Okay, so we talked about physical changes with GRIPAR was our acronym. You've already heard about that in class, and now we're going to talk about OCAR. So OCAR is a way to remember the different types of chemical weathering. You've got oxidation, you've got hydrolysis, carbonation, and acid rain are kind of like one. Okay, and let's get right into it. So chemical reactions usually occur when these different substances, so water, okay, is involved with hydrolysis. Carbon dioxide, oxygen is related to hydrolysis. This is with carbonation. And these acids, okay, when these different substances come in contact with rock. Okay, so no surprise, rock, as it touches a chemical, even a chemical like water, changes, all right? And how it changes is the different type of chemical weathering. So acids might not surprise you. Break down a rock, right? You've all seen sci-fi movies where an acid is poured on something and it melts through steel, right? But bases, which are the opposite of acids on the spectrum in chemistry, can also chemically weather rock too. We'll talk a little bit more about that later on. So chemical weathering changes both the composition and physical appearance of the rock. All right. So what it does is it breaks down the rock on a chemical level. That's the composition. But it also weathers it kind of like mechanical weathering would on the outer appearance of the rock. So let's talk about oxidation first. You are more familiar with this than you know. Oxidation in geology is the process by which an element combines with oxygen. That would be the O, right? Or oxidizing is when something comes in contact with oxygen. Oxygen commonly occurs in rock that has iron-bearing materials like hematite and magnetite. Okay. So this happens with iron-bearing minerals, and it turns a little bit of that reddish color. So if you've ever seen iron rust, it turns like that reddish rust color. That's because it's been oxidized. Other famous examples are the Statue of Liberty, which is that kind of that cool green color. That is because the bronze in the Statue of Liberty has been exposed to oxygen over periods of time and has turned green. So oxidation is just basically if a rock's left out in the air exposed to oxygen, it's gonna change quite a bit. So the red color in much of the Southwest, so kind of around Arizona, you can kind of picture it there. New Mexico, if you ever get a chance to go on the service trip to the Navajo Nation, you'll see it. Is because there's a lot of iron oxide produced in the soil because there's a lot of that in the soil there. So that's oxidation. Hydrolysis is a chemical reaction between water and another substance to form two or more new substances. So water has some unique properties. Water, as you probably know, is H2O. So it has the hydrogen molecule and two oxygen molecules. Now, water, because it has these two molecules with two different charges, can break down substances pretty easily and become a kind of a reactant, right? Become something that dissolves other substances. So it can dissolve acids, bases, solids. Minerals that are affected by hydrolysis often dissolve in water. So water is a great what we call solvent. It's a dissolver of most substances. Water then can carry that dissolved mineral to lower layers of the rock in a process called leaching. We are going to talk more about what water can do and how water can carry substances soon. So hydrolysis is simply put how water reacts to rocks and other minerals. right? So you can kind of see here some rain, some water falling on a rock, and kind of on a much smaller zoomed in level here, you can see these bonds being broken. See how the water is sort of seeping in between the different grains of the rock, and it can break apart those bonds. The rock can kind of fall apart and become a sediment. So a broken apart or weathered rock becomes a sediment. So it looks like sand. So that's literally where sand comes from. It's from rock that's been broken apart. Okay, so leave a rock in water and it'll eventually get broken down. So you see that quite a bit with rocks aging quickly that are left in water. The next letter in OCAR is carbonation. Carbonation is the conversion of a compound into a carbonate. So when CO2 dissolves in water, it creates a weak carbonic acid called H2CO3, or just carbonic acid. So carbonic acid has a much higher concentration of hydronium ions than pure water does, which speeds up the process of hydrolysis. So as water absorbs more and more CO2, it gets this effect which speeds up weathering even more. So you guys hear carbonation, you think about like soda as being, with the bubbles, right? No, that's true. There is carbon dioxide bubbles put into soda to make it fizzy, but that's not the actual geologic term when we talk about carbonation. So this is a limestone cavern. So if you've ever been to like Howe Caverns in central New York, this is kind of what it looks like, right? So you guys can see these cool, stalactites and stalagmites. Well, where do these come from? This is mostly limestone, as I said. So limestone, it's mainly made of calcium carbonate. It reacts with water really well. So water slowly kind of breaks all this rock down and forms this cavern here. So it takes quite a long time, but it's all because water has sort of been trapped in this underground area and has broken down the rock. Now eventually, the upper crust here below the surface of the soil, right, where like someone might be walking up here, can get so thin that this cavern becomes a sinkhole. Then, right, so it kind of sinks in, and that's mainly because of the carbonation process breaking apart. Usually specifically limestone, because limestone reacts with water more than other types of rock. Okay, so the last two letters of OCAR are acid rain, or acid precipitation, to be a little bit more exact. Acid precipitation, such as rain, sleet, or snow, is a concentration with a high concentration of acids, often because of the pollution of the atmosphere. So the acid gets into the atmosphere because it's been put there by burning mostly. Acid precipitation weathers rock faster than ordinary precipitation does. So rainwater is slightly acidic because it combines with small amounts of carbon dioxide. Basically, we've got factories and whatnot, right? And these factories put particulates and pollution in the air, adding extra carbon dioxide to the air, making rain clouds with extra carbon dioxide, which drop rain, and in that rain is, you guessed it, extra carbon dioxide, right? So it kind of does what we just talked about before with carbonation, and add kind of an accelerant almost to the acid weathering down all kinds of substances. So acid rain has been greatly reduced since power plants have installed these scrubbers, which are kind of cool. They remove much of the sulfur dioxide before it can be released. So essentially in the smokestacks, they kind of have these little materials that absorb a lot of the sulfur dioxide before it can get out into the atmosphere. But when fossil fuels, especially coal, are burned, nitrogen oxides and sulfur dioxides are released into the air. These compounds combine with water in the atmosphere to produce nitric acid, nitrous acid, or sulfuric acid. So fossil fuels, we talk about those, you should recognize we're talking about gasoline, kerosene, natural gas, all that stuff. It adds a lot to the atmosphere in terms of acid rain. So it particularly happens more where we're burning more of the stuff. I'll show you a couple maps in a minute here. So this is just a chart to show pH scale. So pH scale is sort of the measurement of the amount of acidity in a substance. So as you can see, it's more acidic up here, neutral meaning no acidity, and then more basic is the opposite of acid or of an acidic substance. So ocean water, your Drano, our bases, and all the way up to battery acid is the strongest stuff we've got in the pH scale here. So acid rain, you can see, has a lot more acid. It's a 3 to 4 pH versus just regular water. Normal rain is 5, 6, and 7. So when acid rain gets going, it adds a lot more acid to the water, which does increase weathering. Okay, so here's just a little graphic of how this happens. There's the smokestack, there's the sulfur oxide, nitrous oxide being added to the atmosphere. So these, condense to form clouds, and that acid's got to go somewhere, so it's falling down, and it's affecting plants, and it's affecting structures on the earth, which I'll show you in a second. Okay, this diagram makes it really easy to see kind of how we've changed and how much more acid has been entered into our ecosystem. So before 1880 here, we're looking at the pre-industrial revolution, right? So this is not too many factories were around. We were just sort of ramping up our production of fossil fuels and greenhouse gases. And you can see that higher pH there means there's less acid, right? Even on the low end, this is the remember, because the lower the number, the more acidic it is. So a little bit more on the low end here, but for the most part, most of the acid was able to be absorbed, and the acidity of the soil, the pH of the soil, is 6, which is just kind of right around what a plant wants to grow in, what a tree wants to grow in. So plants could grow pretty well. So you go 100 years later, we've been burning tons of fossil fuels in power plants. We've been driving cars around for a long time, and we've added a lot more acid to the atmosphere. And you can see the average pH of water is up to 4, and look how much more acidic the soil is. So that makes it harder for plants to grow, and in some places actually kill some plants. Here's just a quick example of sort of that acid burn off of plants. So here, plants had a hard time regrowing or sustaining growth because the soil is too acidic, and even some of the foliage from the plants took damage from the extra amount of acidity in the rain. And acid rain can also affect man-made structures as well. So this is a statue, obviously, that's exposed out into the rain, and it's made from limestone, so kind of like that cave I showed you before. And as we said before, the acid rain would fall, and it would have that little bit of extra acidity in it, and would break down statues and things like that. Think back to the Statue of Liberty. Now this is a little bit different since it's made of rock and it's kind of being broken down, but it's still being exposed to these elements and the extra amount of acid. So this map also kind of just gives you another sense of it. Look how much lower the pH is in this area here versus out here. What's the main difference? Well, this is sort of where there's a lot of factories, right? This is called like the Rust Belt in here, where there's lots of steel production and other areas, factories that burn a lot of fossil fuels. Also, there's a lot more people that live in this area here too. So there's more people, they're using more energy, adding more pollution to the atmosphere, producing more acid rain. Okay, so this is the lecture for Unit 3, Lecture 2. I hope you enjoyed it. You're still awake. You can go back and double check it a couple times if you need to catch anything you missed, and study for your quiz. Hope you have a good night. Thanks. Bye.